Welcome to the second webinar where we're going to be doing quadratics and algebraic fractions, and just quite intense today. There's quite a lot involved in this topic, and it's a very high-end topic. It's very much the very top of GCSE and where AS level starts. So in terms of trying to gauge how difficult this will be, if you've not come across quadratics before, you might find it quite challenging today. We've just got someone else joined us. Cheryl, this is secondary maths webinar. Is this where you intended to be?
Oops, no.
No worries.
I'm primary. Thank you. Bye.
Bye.
Maths is the place to be this morning.
Sorry?
Maths is the place to be this morning.
It clearly is. I must have done the announcement, maybe like to everyone or something. I'd say, don't mind. Yes, so you will probably need a pen and paper because there's quite a lot to do, and we'll get started. So, sorry, that was a bit bright, isn't it? Early in the morning. So, a quadratic is basically also known as a binomial in that it's a type of polynomial with two brackets or an x squared term. So to get that x squared term, you have to multiply out the brackets. So we did look at this. I think it was when I saw you at the Institute, wasn't it? In terms of expanding brackets, we need to think about every single bit. So whether you think about FOIL, which is first outer. So first is that one. I'm going to go. So first, you get x squared. X squared. Outer is 4x. Inner minus 3x. Last minus 3 times 4 is minus 12. And you can put all that together. So that you can collect these two terms together. So that when you expand the brackets, you are left with a three, that has three terms. So if you guys have a go at doing the other three, just to get you mentally warmed up. I think all of you were able to do this, aren't you? But let me know if there's any issues. There we go. Okay. So put your hand up when you have done those. So Hugh, what did you get for the first one?
Number 2, I expanded it to x squared plus 5x, take 4x, and take 20, which simplifies down to x squared plus x, take 20.
Yep. Good. And Sam, what did you get for the next one?
2x squared minus 4x minus x plus 2 equals 2x squared minus 5x plus 2.
Yep. And Matthew, done the last one?
Yeah, I just did 2 brackets, x minus 4, and
Yep.
then got x squared minus 8x plus 16.
Good. Excellent. So is that all fairly straightforward, and any issues with expanding brackets? No?
No, it's fine. I've been doing a lot of practice with the year 9s and 10s.
Great. Excellent. Okay. So I put the AS maths up here, but often, I mean, it totally depends on where your kids are for GCSE. A lot of them won't be taught any quadratics. You know, all the sort of B, C and below won't be taught any quadratics, just, you know, because it is considered the most complex and it's quite a big field of stuff. But as you say, you know, you do the expanding brackets, and on all the papers there's the expectation that they can expand and factorise, which students who can't just see it find very difficult in a sort of, you know, what are you doing kind of way. But at AS Maths, they have quite a lot to do. So there is sort of the basic things of collecting together terms. We're going to be completing the square and using that to tell us about the graph. We're going to be thinking about the discriminant, which is to do with the quadratic equation, the quadratic formula rather. We're going to look briefly at inequalities. Not sure if we're getting to substitution of some things, but we'll see. I think we should get onto these. But it's quite involved, basically. Now, sorry, this is me then comparing the new GCSE to that. So they have to expand products of 2 or more binomials. Well, it seems unlikely that they're going to get them to do 3 brackets, but even so, it would just be the same process. Factorising, including ones that have a number in the front, which they find very tricky. Thinking about what is happening graphically, and it does say finding turning points by completing the square, so just the same as AS. And I do remember doing completing the square at GCSE, but then it seems to sort of drop out of sight for quite a lot, well, for the last 20 years. Know about the graphs, solve quadratic equations using all of those methods. It is really very similar. It even solve linear inequalities and quadratic inequalities. However, generally, as it says, using set notation on a graph, in terms of inequalities, the students would generally be asked to draw the graph, plot it, basically, and look at it to be able to solve an inequality. But it's very similar at the new GCSE. It's been really raised, the standard's been really raised to be basically not far off AS level. So, oh, hi Mark. Sorry, we've started. So far we've just done expanding brackets and talking about what's in the curriculum. So we were just doing the expanding like we did a little bit of at the intensive study week. So 2 brackets and multiplying them out. Now we're going to look at the opposite way around. So factorising. So we've got a quadratic equation. Who knows, why do we do factorising? Anyone know? Sam, you've still got your hand up on the page, so I don't think I do. you know why we factorise a quadratic equation?
Solve it.
Yeah. And what does it mean to solve something?
To work out what x is.
Yeah, absolutely. And that's algebraically, this is me, pushing it, this is, getting more and more tricky as we go. What does that mean when you think about things graphically? Does anyone know? Yeah. Is that you putting your hand up this time?
Yeah, I've actually tried to do a bit of revision because this was completely alien to me.
Right.
It's where it crosses the axis and the turning point.
Right. Yes. So factorising, which means we do to find x, well, it helps us to solve and find x. You're absolutely right. It is the where it crosses the turning point. We will actually find by completing the square, or with a quadratic, it is symmetrical. So the turning point is always exactly halfway between the 2 points that it crosses. So solve an equation and to sketch a graph. So that's basically was what you were saying. So solving an equation is, the idea is simple. Think about two numbers that multiply to give 0. In order to do that, hopefully, one of those had to be 0 itself, because anything else multiplied together won't give you 0. So that means that any two numbers multiplied together, then either A must equal 0 or B equals 0. So when we have a quadratic, we factorise it into two brackets and it's equal to 0, then that means that either x minus 2 equals 0 or x plus 5 equals 0. And we use that in order to then rearrange that so that the 2 goes over so that x equals 2 or x equals minus 5. So the key thing that, do you know what, I forgot my first time teaching quadratics. I could not figure out why I could not get the answer that I was expecting. And it was because on the right-hand side of the equation there's still a number. So I've managed to factorise it and leave a number over here. You cannot do that. You can only factorise the quadratic once it is all on one side equaling 0. That's the only way that we can then say that one of those must equal 0. The kids fall into that trap all the time, completely forgetting to bring it over. So they'll factorise and it'll still equal 2, and then they'll be like, oh, therefore x minus 2 equals 2, or x plus 5 equals 2. But it doesn't work that way, because that's not how it works when you multiply two numbers to get 2. That could be all sorts of things. So it must equal 0 in order for this to be true. So, just as an example, x squared plus 14x plus 24 equals 0. Just wondering if I click straight away this. How do people like to factorise? How many people have taught this? Okay. So I'm not surprised, because obviously this is, as we were saying, higher end of GCSE, and you've already did something, so I'd be very surprised. But when I was taught to factorise, I was simply told you need two numbers that multiply together to give the low number at the end, and those same numbers need to add together to get this, which you see all the time. When you've done it, you can then multiply back out and see why that works. And we weren't told any more than that, and it was simply a case of trial and error. So you can just go through writing down, okay, so I've got 6 and 4, I've got 12 and 2, I've got 8 and 3, you know, so you could write them all out. Generally, as you go, you're like, oh, hang on, 12 and 2, oh, that's good. I know that we'll make that. Now, a lot of students really struggle with this because, well, for a start, because they don't know the times tables very well, so they struggle to find these in the first place. But they also struggle to relate multiplying and adding together. They're just not, their processing is not fast enough to identify that, oh, look, I can see this pattern of 14. That takes a great deal of sort of experience. And a lot of students find that they just have to write out all the options, and then they'll then sort of add them all together to see what they get. But that does require them to have also written down all of these as negatives as well, and so on. They don't really have to consider that in this case, it's all plus. Before they can then identify that when you factorise it, it should be a 2 and 12 in there. And then it's always good to get them to multiply it back out again, just to check x squared, 2x, 12x makes 14, 2 times 12 is 24. Because so often I see them, there's one in particular, which one is it? It's something like, I think it must be 12 or something, where it's 4 and 3, or 6 and 2, and no, it's when you've got to get a 6, and they've got like a 5 and a 6 and a 1, because they want to get 5, and they've done a 3 and a 2 to get 5. And it's so totally dependent on the signs, and because they haven't multiplied it out again at the end to check, they just leave it and move on thinking that they've done it correctly, so it's always worth checking. So that means we can simply find out that the solutions, I mean, the kids can then write the next step if they wanted x plus 2 equals 0, or x plus 12 equals 0, therefore x equals minus 2, x equals minus 12. But it's fine for them to just jump to that. So, oh, I want to raise that bit. It becomes a little bit more complicated when there's a number in front. Because here we've got the option that as well as the bits at the end, we could also have at the front of our brackets 2 and 2, or 4 and 1. So you're kind of thinking, okay, so I've got to go through trial and error with these ones, and through trial and error with 4 and 1. And again, you know, a lot of students are able to simply run through all the possibilities very quickly, either writing them down or in their head. Now, to multiply two things together to make 5 is quite nice, because of course we know we've only got the option of 1 and 5. So we know that somewhere around here there's only 1 and 5. So we can simply just try it with this and see 5 times 2 is 10, 1 times 2. We got lucky. And because the plus here, the minus here, we know we want to take both those away, and 2 negatives make a plus. There is another way, which I will show you, I think, on the next slide. So let's just go through this first, just type it in rather than scribbling here. So don't, if this is the first time that you're really coming across this, do not be surprised if it takes you a long time to go through all the possibilities. And also to see that there are other possibilities, because you could get very stuck thinking, okay, I need a 4 and a 1, and going through endlessly looking for possibilities, because you're like 20 and 1, oh no, 5 and 4, no, you know. So you can't quite get anywhere with that. There must be another possibility. Now, here, this is where some of the students make mistakes, because what they've not realised is that when they're doing this bit, they're making x plus 2 equals 0, and then solving that tiny little linear equation that they've got. They think they're just switching the sign, and thus they forget this bit that's in front of here. So it is safer to get them to write out each bit. I'd do it without the brackets though, because the brackets are kind of holding you back a bit. So either 2x minus 5 equals 0. So we can rearrange that, take the 5 over the other side, divide by 2, so x is 5 over 2, 2.5, and x is a half. So key to sort of get that across early, I would always include this line when they're starting, so they don't basically form a misconception, which is what happens, but they don't really understand what they're doing. They don't realise that we're considering either this is 0 or that is 0, because one of them must be 0 to multiply to get 0, so we can solve that little equation. That's quite key. So there are some resources that I have uploaded onto Student Central, which you can get students to go through. There's like an initial investigation, or there's quad 1 and 2 have bubble steps, which just sort of say do this, do this, do this, which can be good for the younger students, or teaching for process first before understanding, which is one of those things that you just need a lot of experience doing, so it can be sort of quite good well. I've got these 2 slides that I've put in here. Is that the same one in here? No, it's not. So this one thinks about factorising it, and it gives you each step. So it sort of says, okay, I need 2 numbers which add together to make 4, multiply together to make minus 12. So it's written them out like this. There's 6 plus minus 2 is 4, and 6 times minus 2 is minus 12. Lovely. So that's gone straight into the brackets. And then it solves it. So these are just these that I'm wanting to show you a bit more. Yes, this is what I want to show you. This little process here with the what do you call it? Trial and error bit. Here, they're trying to find, when they've got a number in front of it, what they're trying to find is 2 numbers that add together to make the 3, but they now want 2 numbers that multiply together that make not just the minus 5, but because you've got this number at the front, you can do it by multiplying by that number at the front. This process is often called split, factorise, collect. So I call it the SFC method with the kids. It's split, factorise, collect. So the first thing, the split, is the fact that we are going to want to split this middle term into the 2 things that add it together. So we first of all need to identify the middle term, which is 3. We need 2 numbers which add together to make 3. But because of the way that the brackets work when you expand them, this thing that we need to multiply together is actually not just the minus 5 now, because we end up with 2 times that minus 5. We need to look for a number that multiplies together to get minus 10. So there's still this trial and error bit. We're now looking for numbers for minus 10 and 3. So 5 minus 2 is 3, and 5 times minus 2 is minus 10. So we've found our numbers. So what we do is we break the 3x up into the 5x minus 2x. We split the 2 terms. We then collect together. This is a bit weird, but that's a split, factorise, collect, isn't it? Should be maybe split, collect, factorise. We then want to, well, it doesn't matter actually, we can factorise, no, it is factorising for next. We've split it into these two bits, and then we're going to factorise out. So we're going to consider this chunk here as 1, and then this bit here as the other chunk. So we factorise this bit. Now the common factor is x, so we take the x out and we're left with 2x plus 5. And then we've got this bit here, minus 2x minus 5. If we take a minus 1 out, there should be a minus 1 there, that's silly. Then we're left with, again, 2x plus 5. Now that means that we've got x times 2x plus 5 minus 1 times 2x plus 5. So from that, we can factorise out 2x plus 5, placed at the front, and we're left with x minus 1. And that has, with slightly more process and less deep thinking, got you to this solve, basically. I perhaps have not made that completely clear, so I'm going to go through it with another example. Has anyone seen this method of factorising before? No, okay. Who had seen factorising before? And had you guys always just done it by trial and error?
Yeah, trial and error.
Yeah.
Yeah, trial and error again, but I've only really got to grips with it over the last 3 or 4 days whilst trying to revise it up for this.
Yeah, no, absolutely. And, you know, I had never come across this method until one of the students said to me, oh, why do you teach us this way, which isn't really a way, it's just us spending absolutely ages trying to figure out what we're doing, when I was taught this other way at school, where I just do this, and showed the whole class, and I was like, okay, that's quite clever. So let me show you a bit more smoothly what I'm trying to show. Is about the solving bit. No, we're not thinking on. But anyway, sorry, this is just it solving it. Again, this is the bit, but this is quite nice, this way this slide does it, because it highlights exactly what I was saying to you about the fact that they think it's just minus 5. They don't realise they've got to solve that little bit. And then, what I want to do is go back to this messy slide. Let me do that. Right. Where's this? Right. In fact, no, I'll show you on this way. We can do it on all quadratics. It doesn't actually have to have a number at the beginning. There always is a number at the beginning. It's just that it's simply 1. So we need 2 numbers which add together to get 14, and 2 numbers that times together to get 1 times 24, which is 24. So we identify, and there's still this little trial, there is always still a little bit of trial and error, but we identify this. We can then, but we can split our 14 into 2x and 12x. So that is what we're talking about with the split bit. There's still the little bit of I'm trying to figure that out really badly. Now, I look at this bit here, I factorise that. X is the common factor in that. I'm left with x plus 2. And then I look at this bit here, and I factorise out 12, and I'm left with x plus 2. And you know that you've done this correctly, and this is what the kids like, because initially, for these basic ones, this seems like a very long-winded way to do it, you know, and hopefully most students can just jump simply to the x plus 2, x plus 12. But this is an excellent check because it means that if you've then ended up with the same ones in those, you know that you've done it correctly, and you can simply draw down the other bits, the x plus 12 and x plus 2. So obviously seems very long-winded for this because we haven't achieved anything more than we did here. But for the more complicated ones that have a number in front of them, and the students have quite a lot of different options available to them, it's a bit better because we're looking for two numbers that add together to make minus 12, and we're looking for two numbers that multiply together to make 20, because we do 4 times 5. So looking at those, 10 and 2, but we want them both to be minuses, and minus 10 and minus 2. And then I can again write this out, just splitting that middle term, the 12, into minus 10x minus 2x plus 5. And it doesn't matter which way round you write this. If I put the 2x first then 10x, I'm just going to get slightly the brackets the other way around, that's all. So I look at the first bit. I can take out, and this way they have to also remember their basic math, I can take out a factor of 2 and a factor of x, and I'm left with 2x minus 5. And then I look at this bit here, and I made a mistake, did I? No, that is right. Minus 1 gives me 2x minus 5, isn't it? Minus and minus. So now I know that draw down the 2x minus 1, so that's the collect. So that was the split into 2. There's the factorise, and this is now the collect. It's 2 bits. Students prefer this because it is a slightly more passive method, but it can help if they're just getting a bit stuck along the way. It's just another way to show them. Right, let us move on to that. Yeah, do you have a question about that, Matt?
Yeah, sorry, it was about the last example you just did.
Yeah,
the third step where it says 2x minus 5.
Yeah.
How did you get to minus 1 brackets 2x minus 5?
Yeah, it is quite a difficult one when it's a 1, because I was thinking, oh, what do I have in common? I don't have anything in common. So what I then thought was, I know the bracket should be the same as that one. So basically, I put the bracket there, which is why I was going, oh, it doesn't work. And then I realised that if I put the bracket there, in order to get that one, I need to multiply by minus 1 outside. Not the easiest of ones, actually, as an example. And you have to very much decide that if your students are all getting on very well with just using trial and error with these ones for numbers in front, then don't worry about showing them something that can seem more complicated. Because in this case, when it's a minus 1, it's quite tricky. But had it been, like 4x plus 10, we'd have again known to take a 2 out, hopefully, and then realise, hang on, we've taken plus 2, but that's not going to be a minus. That needs to be a minus. So I think the other reason the kids find this is that they don't have to think about signs so much. A lot of them get really wrapped up thinking about the signs rather than the numbers. So they're thinking, rather than attaching the signs, keeping the signs with the numbers, it's like a distinct thing. So they're like, oh, if it's a plus and a plus, then they must all be plus. If it's a minus and a plus, then it's got to be two minuses. If it's a plus and a minus, then you're going to have one of each. You've got to figure it out. And if it's a minus and a minus, we'll say the same again. So they spend a lot of time worrying about the signs, but it shouldn't be something they actually have to think about. It should just fall out from thinking about this as minus 12, rather than thinking about it as 12 and then worrying about the signs. So I know a lot of people do sort of do it with the numbers and then worry about the signs, but I find that quite unhelpful in terms of what you're trying to get to. So at some point have a go yourselves at trying this slightly weird method. Well, would you like to have a go in first? You see what I thought. Well, actually, this is just an aside. When presented with these, and they often do this sort of in an exam, students forget. They think, oh, okay, right, okay, there's quadratic, need to get it into two brackets. So I think one of the good things about the split factorised collect is it means that when they see a two-term quadratic, they are aware they just need to take out a common factor. So don't forget that you can always just take out a common factor. Don't forget that it's also the number as well, rather than just the x. What about this one? They're generally not too mean, but often you can take the 2 out. You may not actually be able to factorise the equation. And what does that mean? If you can't factorise it, what does that tell you about the solutions?
It's not quadratic.
No, it's more that it's so when you factorise, the answers that you get are always whole numbers. Well, not whole numbers necessarily, but rational numbers. So you could get a half, or 5/2, or third, isn't it? If you can't factorise it, then it means that it is not an exact answer. You can still solve it, but just not by factorising. So 3 methods: take out a common factor, difference of 2 squares. We briefly looked at one at the beginning, but that's basically an example. Oh, no, we didn't actually do it. We looked at repeated one. I think I might have actually gone on to the next slide. I got ahead of myself there. This is the difference of 2 squares. So it's when one bracket, the brackets are the same except the sign is different. And what ends up happening is they cancel each other out. So the x squared stays there. We then get a minus 4x and a plus 4x. So they disappear, leaving us just with the minus 4 times 4, which is minus 16. So you need to be able to spot things that look like that. Something that has an x squared and a square number with a difference of 2 squares. Trinomials are what we keep talking about. So here you go. Yeah, if they're positive, the signs are the same. If they've got to turn negative, one's different. And you have to just find a pair of factors. Check it. Here we go. I thought I'd done a bit about difference of 2 squares. So difference of 2 squares, you need to be able to spot these. Then the quick thing to spot these. Obviously, that starts with knowing what squared numbers are and recognising them, spotting them straight away, so they think, oh, there's a squared number, and I'm missing the linear term. So it suggests to me that I need to split this one into its squares. So 81 is 9 times 9. So I'm going to have 9 in each bucket. And I'm going to have y squared. And in fact, you're helped by the fact that it's a negative. So in order to get a negative, it must be a positive and a negative times it together, because if it was the same sign, it would be a positive. So it doesn't matter which one's which. So that's the difference of these squares. And if you just check it, you get 9 times 9 is 81, minus 9y plus 9y, cancel out, minus y squared. So have a go now at doing these things. Factorising. So just put your hand up when you've done those. So Sam, what did you get for number 2?
Split the 4x and I've got 2x plus 9 and then 2x minus 9.
Oh, now multiply that out to check.
Oh yeah, sorry, yeah. It's got to be a 3, hasn't it?
Exactly, yeah.
Sorry.
No, it's fine, that's great. I mean, that's exactly it. You see, these are particularly mean. Often the students at GCSE wouldn't have that. They just have x squared minus 9. And it's just to get them to recognise this pattern, that you're basically having to sort of square root both bits. Yeah, so 2x was 3, 2x minus 3. Right, Matt, what did you get for the third one?
I got 3, and then in brackets 1 plus, and then close brackets, and another bracket, minus 2x.
Yeah. So you take the 3 out first, because this is a mean one, because if it wasn't a big think, you'd be going, square root of 3? That's not a square number. So you have to take the 3 out first, and then you've got 2 square numbers. Whereupon it's just the same. You can then square root each of those to get the 1 plus 2x, 1 minus 2x. And Mark, have you done the last one?
Oh, sorry, I'm still thoroughly confused over the second one.
Okay, that's fine. It's only because your hand was up, so I wasn't sure if you would.
Oh, is it?
Yeah.
I don't think it was.
So
I solved the first one quite quickly, and then thought, "Oh, great, I'm done," and then realised I hadn't done the other 2. So
that's fine.
Is my hand still up, or is it? Is that up now? Or no,
No, no, yeah, so now it's up again.
Oh, hang on. Right, okay.
Click
I
it
didn't
again.
realise that. Hang on.
Alright.
Right, you've still got about a dozen screens of autograph up, and I'm getting myself confused.
Alright.
Okay, cool, done.
So, hazarding a guess at the fact that, I mean, this is extra mean. So, you don't have to, but if you think about the pattern is, we're basically square rooting each bit and putting it in a bracket. What is the square root of 9x squared?
It's going to be 4x, isn't it? Sorry, 3x.
Yeah, 3x, yeah. And then the square root of
Has to be
16y squared.
4y.
Yeah. So you've just got...
So,
You go on?
no, so I'm looking at it again. I figured out it's something to do with 3x and 4y. I'm just trying to figure out how to get the minus 16 bit now.
So if you basically make one of those plus and one of those minus, just like that.
Oh, I see.
So that's
Yeah,
what you do.
I see. Yeah.
Yeah. So square root each bit and have one with a plus and one with a minus. This middle bit cancels itself out, and we're left with the minus 16, the 4, the 4, and the y. So tricky. I mean, that would be quite tricky if that was to come up at GCSE. I'd be quite surprised. But good to see. Okay. What about if you see one that doesn't have a minus?
Surely that just means that the whatever it is, both signs are the same, doesn't it?
Oh,
so it'd be x.
Yeah.
X plus 2 is x plus 2. That will work.
But that would work to get 4x. Yeah, ultimately, it can't be factorised. And in fact, you wouldn't need to factorise it because you could simply just solve it if it's equal to 0, for example. It would then just equal, oh no, that's not going to work. No, that one cannot be solved. Because x squared equals minus 4, you can't then square root it. So you can't solve this one in high school maths, basically. Because it's imaginary and you don't need to know anything about that. And the kids will ask you at some point what happens when they square root a negative. Some of them will just ignore the negative, square root it, and then bung the negative back on again. That is not possible. It does not exist in the real numbers. And what that means graphically is it doesn't cut the graph, basically. Sorry, it doesn't cut the axis. The x squared equals 4 is 5. Yeah. So when we are solving a quadratic, I'm just about to talk to you about this, so I will not get ahead of myself. We're talking about where it cuts the x-axis. And in this case, it doesn't cut the x-axis, so you cannot solve it. So here we are. Here we want to draw this graph. This is the one that we originally factorised. In a blink of an eye, you should see it factorises to that. And then you didn't do it. But you factorised it, and now we know that this graph could simply be written as this graph. They are exactly the same graph, just written in a different way. And that helps us to draw it, because we know when we solve this that either when we're solving it, what we're doing is we're making y 0. Y equaling 0 is the x-axis. So all along the x-axis, y equals 0. So when y is 0, x is minus 6 and x is 2. So those are the 2 points where the graph crosses. The x-intercepts. And that helps us then to draw the graph or sketch the graph. Generally, at AS level, you're only asked to sketch graphs showing the key points. Now, the key points are the x-intercepts, which we find by solving, and the y-intercept here. We can see is when x equals 0. So on the y-axis, x is 0 all the way along. So if x is 0, that bit's 0, that bit's 0. So it must cross at y equals minus 12. So we're expected to just mark those 3 points on. And then to know that a quadratic graph is what we call a parabola, this curved shape that goes through those 3 points. So a sketch would involve a smoothly drawn curve that had all those done. Now I tend to suggest to my students that they draw the curve first and then draw on the points. Well, it depends how you do it. So that's how solving relates to finding the x-intercepts. And when x is 0, we can find the y-intercept. And that helps us to sketch this. So here are a couple. Do I do 3 of them? Yes, I do. I'll do the first one, shall I? So factorising, just a quick reminder, you're looking for 2 numbers that multiply together to get 60. That add together to get minus 4, minus 60 and minus 4. So, what do you think? 15, no, 6 and 10? Yeah, 6 and 10. So, it's going to be plus 6 and minus 10. And it's going to cut at minus 60. So, it's also a positive x squared, which is a U-shaped graph. It's going to go through minus 6, 10, and minus 60. There we go. Any questions, confusion about what on earth I'm doing or anything like that? Okay, can you guys then do these next two? So factorise, identify the y-intercept, sketch the curve. Just get up and walk around to step back. Right, Hugh, describe to me your
Graph 2, it's sort of like an upward parabolic, so it goes from minus 1 on the x-axis up through positive 6 on the y, then back down to positive 6 on the x.
Yeah. Cutting it 2 and 3. Yeah. So the fact that quadratic graphs are symmetrical also helps the students to draw them, and they get marks in the exam for how the curve looks. So as close to these beautifully drawn ones that autograph can do as possible is what you're aiming for. A lot of them get sort of hung up on sort of, they sketch a bit, they draw a bit more, and it looks really sort of liney, lots of lines together. They've got to practice, basically, putting these points in and drawing a smooth curve through it. It is, you know, like everything else in us, another skill for them to perfect. Who wants to tell me about number 3? Matt, you got your hand up? Or Mark?
Yeah, I thought I just realised I actually got number 2 wrong when Hugh was going through, so I'm just rechecking number 3. I think it's going to be a U-shaped parabola.
Yeah.
I'm a bit confused because I've ended up with x minus 4 by x minus 4.
Yeah. Yeah. That's right. So what do you think that looks like?
I'm not sure how it's going to go from minus 4 to minus 4, because that's not going to intercept the y at all, is it?
Right. So what do you think it does instead of, doesn't cross it, doesn't cut it? Instead, it is what we call a repeated root, because it's the same one. And that means that it just touches it. So yes, curve cuts the x-axis at 4 twice, but because it crosses under and over at the same time, it basically just touches it. So that was a bit of a mean one. Yeah, it's a bit of a mean one. So if there are 2 distinct brackets, it's going to cross and then come back. But in this case, it is just sitting on it. So a repeated root.
Yeah, that makes sense. So effectively, does that work for every single occasion where it's like if both the minuses are the same, or both, well, it could be minus or positive, really, couldn't it? If they're both the same in the brackets, it's just going to sit on it.
It is, yeah.
Okay.
So yeah, 2 separate brackets, it will cross. Repeated ones, it touches. Yep, always the case.
So really, sorry. So, if you're going for the you've had to do the whole completing the square thing, because then you do normally end up with just one set of brackets square, don't you? So that will always sit.
That is slightly different. That's not giving you the x-intercepts. Factorising gives you the x-intercepts. Completing the square gives you something different. Let us get onto that in fact. I think. Hang on. There we go. Yes, we'll get to complete the square in a minute. I'll just let me this is just about vocabulary, really. When we factorise, we are saying that x minus 3 is a factor of the quadratic. You know, like when we talk about the number 12, 3 times 4, 3 and 4 are both factors. So if you find a factor, then the opposite way around gives you the x-intercept. So if we know the x-intercept, we can go the other way around to get the quadratic. So what this is saying is that if you have a graph but you don't know the equation for it, you can get it by looking at each of the x-intercepts and putting them into a bracket with the opposite side to get the factor. And we can only have 2 of those, so it will be both the intercepts. The only difficulty with that is that we're always going to just put them into brackets like this without any numbers in front, because that's what's simple to do. Whereas in fact, there might have been a number at the front. So there could be different curves. But what it means that you'll get is that you get a family of curves. So this is the same as this, it's just multiplied by 3. So it's just stretched up by a factor of 3. As it says, there are infinitely many parabolas of this form. But that's just a little bit of the extension. Now, so to find the equation for this curve, you can come up with anything really. But the very basic one, what would the very basic one be? You can give it to me in factorised form, obviously. So what's the equation of this curve going to be? Look at the intercepts and put them into, Mark.
Is that, it's going to be something like k open brackets x minus 5 close open again x plus 1 close, something like that. It's going to be something along those lines, isn't it?
Yeah, absolutely. Ta-da! Excellent.
Yeah, I'm learning.
Yeah, there you go. Absolutely. This is a bit more advanced for the kids. And at GCSE, they would never be asked to come up with one that wasn't just the basic one, where k is 1. Really. Anyway, this is going to be the same again. So, just they just come up with one that's very simple. I'm hoping, it's going to go on and on and on. I think we're going to skip through this because you can do this a bit more in your own time. And I might just find this one. There we go, that's what I wanted, this one. So, going back to what we were saying, what is the equation for this? Oh, I've lost my arrow. For this one. Matt, is that your hand up, or is it just still? Yeah. Or is that now your hand up? I'm very confused. Matt, your dog's anyway?
Yeah. Is it the x minus 3 squared?
Yes, yeah. So the same bracket is repeated, x minus 3, is sitting on x equals 3. Good. Now, what about this one here? What do we know, first of all, about the parabola being this way up? Mark?
Yeah, it's going to be a minus x squared, isn't it?
Yeah.
Because that's the bit of inverted parabola.
So minus x squared. Well, all of you just have a quick think of it and see if you can write down the equation for this based on what the factors are. Now the first one that I tried didn't work, and the reason it didn't work was when I then multiplied out the brackets, I did not get this the right way. I got minus 7, so that I know that I put my minus in the wrong place. That's just a hint for where that goes. So what equation have we come up with? Yeah, Mark?
Yeah, I must admit, I'm having a couple of difficulties with this. I started off with x minus 7 x minus 7 x plus 1 in brackets.
Yeah.
But I know it's got to be a minus in there, which is the bit I've just realised. I think that's why I'm going slightly wrong.
Yeah.
Because it's got to be. It's going to have to be the minus one. You have to be minus x in brackets, isn't it?
Yes, one of them has got to be minus. So it doesn't matter. Whichever one that you make minus, you've then got to make the other symbol the opposite. The other sign. So for example, if you've got x plus 1, it'll need to be minus x minus 1, because when you then solve that, it'll give. Oh no, that's the wrong way around, isn't it?
Yeah.
But yeah, the other way around.
Yeah. So if I had the minus x minus 7.
Yes.
And then the x plus 1, then that will give me my x squared plus 7x, and give me a plus 7, won't it?
But you'll have minus x.
Sorry, minus x squared plus 7x plus 7. It'll flip, I'm confused now.
I've got minus x squared plus 6x plus 7. Because the first one I tried didn't work.
Yeah, that's right. Sorry. Yeah, sorry.
Yeah.
Yes. Yeah, because it's the minus x minus 7. Yeah, that makes sense.
Yeah.
I know.
Yeah, because you've got to think when you've then taken it out of the brackets and equal 0, it's still got to equal x equals 7 to get it to solve it. So, as you can imagine, this is not something that the students have to do, because it is quite tricky. But it helps them sometimes to do it this way. And these are quite good things to do. You know, there's a card matching. I think these pictures probably come from them, you know, where you can match together factorized form, Peters square form, the graphs, the intercepts, all of those bits. I'll show you a big picture of that done later. And if we were face to face, then I'd get you to do it. But it's just being able to get your brain to move from the algebra written word symbols to this graphically. And it is much harder suddenly when things become negative. Students don't like it. It kind of feels wrong somehow. I suppose that's why it's called negative, because it has these sort of negative connotations and feelings that come with it. But it's harder, not quite right. And yet you'll probably find that more things in real life are modelled by a negative quadratic. You know, if you imagine bowling a cricket ball, or any sort of any sort of ball where you throw it up in the air and then down again, would be modelled by that. You're unlikely to. Well, no, it's equally you could get it to bounce, but it would be more of a harsh bounce. I think it would be unlikely to be quadratic. Anyway, moving on. Oh yeah, so that one we couldn't see the y answer. Really? Anyway. Yeah, so we need a minus. So they, in fact, have solved this problem by factorising it and then just putting the minus on the outside, which is a much better idea than mine, where I just shoved the minus into one of them and changed the sign around. But it achieves the same equation. Right, on to completing the square. Students find this quite tricky if they are trying to achieve deep understanding and are taught it procedurally. And what I mean by that is the kids that love to just manipulate algebra, you say to them, you do this, 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 they go great, they do it 100 times, they love it. They're not bothered. They don't really care whether or not there is a deep understanding. But the problem is that when you teach things, often trying to achieve depth of understanding when it's something quite difficult to understand, causes them to struggle, so you tend to fall back on the procedural stuff. And I'm not really sure what the solution to that is, because I think I tend to teach quadratics kind of as I'm teaching you, all wrapped up, graphs and algebra and all the different forms all together, rather than this process, this process, this process, because I want them to have a more holistic view. linking together what is happening in the graph and the algebra helps, so that for a start, just with checking, that the answer is what you'd expect. Now this was the one that we looked at earlier, where we factorised it and we found the x-intercepts. So we know that bit of it. We also know, which I think were, what, 2 and 12. We also know, factorisers to give 2 and 12, so the intercepts are -2 and -12, and the y-intercept is 24. Completing the square is, I don't know who discovered it. Just trying to think if I know. No? But you know, people fiddle around with things. And often, completing a square is kind of something that you can imagine one of the kids fiddling around with, but not quite getting there. Oh, I want to switch over. The premise behind it is we want to put it into a squared bracket, and we're just concentrating on this first bit, this bit here. So we halve it, and I realise here, again, I think I've always taught this procedurally and not really appreciated why. I mean, I appreciate why it works as I'm about to show it to you, but I'm not sure how on earth it was invented. You halve this figure here, the linear number, and put it into brackets with bx as its own quadratic. So we're now going to just think about that. X plus 7 squared is x plus 7 times x plus 7. So that's x squared plus 7x plus 7x is 14x, plus 7 times 7 is 49. So that's great. We have now got, in common with our original bit, we've got this bit in common with it. So that's why we halved it, because we were basically doing a bit like the split factorised collect thing. We were splitting this term in two, because we know that if we split it in two, the 7x and the 7x, when repeated, will give us back our 14. Then we've got this issue that we've got this extra bit though. So in order for this little bit here to look exactly the same as this bit here, we need to take away the 49 because we've got this extra 49 added on the end. Now, putting the original 24 back on, there is no difference between what is written here and what is written here. They are exactly the same, just written in a slightly different way. And as I said before, the kids who, you know, are happy to just do what you say are like, great, excellent. So halve it, square this and take it off, because that's what's happening every time. You've always got to take it off. They get a bit confused about that. They're like, well, but it's a plus. They don't want a plus, and when it's a negative, I want to take it. No, this is what's happening here. You are expanding it, and you've got extra stuff that you need to take away in order to get these same first two terms. So that's all you're doing. You're writing the first two terms in another way. And then that means we collect these bits together. What have I done with the Here we have our original quadratic written in completed square form. So completed square form means that you have a repeated root, basically a repeated factor, and a number. And you can then go on to solve that as you would a regular basic linear equation by taking things over to the other side, square rooting, and then x is, oh sorry, I've missed a major bit. When you square root something, when you square root things, you have to think back to the fact that it could have been -5 times -5 to get positive 25, or it could have been +5 times +5. So when you square root it, you've got two possible answers, plus or -5, which we write just like that, plus or -5. So then x is either +5 minus 7 equals -2, or -5 minus 7, which is -12. So that is obviously a ridiculously complicated way of getting our x-intercepts. If you're trying to get x-intercepts, I would always recommend factorising as the first thing you do. Completing the square has other uses. Now often they're asked to do it purely from a algebraic manipulation point of view. But generally, I mean, this is very, very much at the top end of stuff. I'm just going to click through this. Right, so it's not going down. I'm just going to raise this bit so that we can see the next bit. Again, we have a number in the front and it creates issues, except in this case it's quite nice because you can factorise the 4 out, and we're left with x squared minus 3x. I only factorise it out of the front because it's not going to affect this 5 at the end, and I don't want to overcomplicate things. However, when I was at school, I was taught to take it out of the whole thing, but it's not necessary. Now we can complete the square of this bit. Again, it's not particularly pleasant because halving that is going to give us 3/2. Kids often here, again, don't appreciate what they're doing. They're trying to get a repeated factor that when squared multiplies out to get the same thing they had. So they put an x here, or they put an x squared here. They don't think that they're trying to get a linear bracket that is squared. Now, if we multiply this out, we're going to get -1.5 minus 1.5, which is our -3. But we're going to end up with minus 3/2 times minus 3/2. So we're going to end up with an extra 9/4. About 2.25. So we're going to have to take off that extra bit, as always. And now this should have square brackets around all of that, because all of that bit was just this bit that's inside the brackets, and that was all multiplied by 4. But that's actually quite nice. I should put my +5 at the end. That's actually quite nice because I can now see, if I multiply that out a little bit, I can keep the 4 out of the front. So 4. And 4 times the -9/4 means I'm left with just a -9. Yay, much nicer. And there's my +5. So that simplifies it back again. I've still got this bracket that I can't write very well. -9 +5 -4. And here we are again. We can solve it again. I'll take the 4 over, and then I can divide through by 4, so I'm just left with a 1. So I've got a square number that's 1. So I'm going to end up with -1 plus 3 over 2, or 1 plus 3 over 2. Which I can click through and show, which is a bit of a mess. Put down there for the 2.5 normal. Any questions about the process of completing a square? It is something that students struggle to remember, particularly when there's a number in front. They get a bit het up because they don't like fractions or decimals, and they forget about trying to get these 2 linear factors here, and then they forget that they always have to take off this bit, so they're not having it in. Let's hope that I put one on the next page too. Yes. So have a go at doing these, and then we'll have a break off and we'll discuss these things. Right, how are you getting on? The first one. Yeah, Mark.
Right, yeah, I've got I started off with. Do you want us to go through the process, or just what I ended up with?
Well, say first what you ended up with, and then we'll see. Check
Okay,
that
I ended up with the square root. For the first one, I ended up with the square root. Sorry, x is the square root of 18 plus 4.
Yes.
I didn't,
Sorry, I should
yeah, I
have.
didn't actually go as far as working out what the square root of 18 was.
Oh
but-
yeah, no, sorry. I should have said I just wanted you to write it in completed square form. Sorry, because there wasn't anything to solve because it doesn't say equal 0. So just in completed
Oh, okay.
square form. So in
Oh, okay, in
completed-
which case then x minus 4 squared minus 18.
Good. Yeah. Yeah. Just in terms of the way that I have just explained this to you, has anyone seen completing the square before?
Only in the homework that you give us for the lead up to this.
Yeah, yeah. In terms of how I have just basically told you a method and said to get on with it, how does that make you feel? Anyone? You know, are you happy with that? You prefer that? Or you want to know
It's
more?
not so bad, only because I've seen it before. If you're throwing that one at me from Raw today, that might got me a little bit more confused.
Yeah. And the kids do find it confusing. So it's difficult to know whether to teach it from algebra or whether to teach it from a graphical perspective, as I will show you after the break. Anyway, who has done number 2? Sam? What did you get? What is it in complete square form?
In brackets, I've got x minus 3 over 2 squared minus 6.
Oh, minus 6.
I've got minus 9 plus 3.
You should be taking off 9 over 4
Right, okay.
because it's whatever you've got in the bracket, the 3 over 2 squared, is what you have to take off because that's the extra bit that ends up being on the end. So the minus
Yeah, I
9
know,
over,
I know what I did. I just squared the 3
yeah.
from the x. There. Okay.
So yeah, I think it should be did you get 3/4. Anyone else? Or is that just me? Minus 9 over 4 plus 3. I think it's 3/4. Matt, what did you get? Did you get 3/4 at the end or what?
Yes, sir. I got, in brackets x minus 3 over 2 squared plus 3/4.
Good. That's my maths here. And have you done the last one?
Yeah, I have, yeah. I've got 2 brackets x minus 2 squared minus 7.
Yes. Yeah. So take the 2 out first. Complete the square on the little bit on the x5, x squared minus 4x bit, and then bring the rest back in. Good. Yeah, this is something the kids find tricky because as a process it doesn't seem to sit very naturally or come, I don't know, or make sense to them. And I think maybe that is in the way that it's taught, in that I have no greater depth of understanding, I realise now, apart from what it means graphically. And I see why it works, because when you multiply it out you get the same thing, don't you? I don't have anything deeper than that. I don't know if there is anything deeper than that. So go away and have a break. And 5-2, back at 5-2, all right? And we will talk about what happens graphically. Hello, is everybody back?
Yep.
Certainly am.
Good. I also, while I was making a cup of tea, realised that I've been a complete idiot and that I know exactly how they came up with this. And this is because, this is why I just don't think I ever teach it this way around, you know. This is how they tend to do it at GCSE, because at GCSE they only need to know the process. They don't have to understand it at all. And so we often come at it from, this is what you do. And I'm really sceptical about how many of them ever really get it and are able to do it. And it's, you know, sort of so far, so close to their GCSE, they're like, oh, well, whatever. And it's very difficult because you don't have the time to show them all the rest of the stuff. But the reason that this works, oh, they just overcomplicated that last one. The reason that this works is because graphically, this is all related to translations. So, if we complete the square, so we can write this graph as this graph. We are coming at this from an algebraic point of view. And I think definitely telling you this now, I don't normally do it this way round. And I can see why, because I don't think it makes sense. At AS, I go from factorising to the graphs. Then from the graphs, we sort of have a discussion about, right, well, how do we get the vertex of the graph? And then from that, come back to completing the square, not the other way around. So this is the graph of x squared minus 4x plus 9. Hugh, did you want to say something?
No, I just pressed the button by mistake.
Oh, that's okay. If you tried to factorise this, you would struggle, because now looking at the graph, you can see it doesn't cut anywhere. It doesn't cut the x-axis, sorry. But it does cross at the y-intercept line. Having completed the square on it, we can see that in fact, you see the vertex is 2, 5. And that is because, I'm just going to click through because I just want to see what I've done. Yes. So, right, I'm going to go back to this here, where I've written here. This is just some tips about teaching completing the square, where I've written get the students to investigate using a graphing package. That is what I normally do. And there was a document that I've uploaded which is called Completing the Square. And I put often useful to link with teaching translations. I think it should definitely, not on the basis of having done it now, I normally teach it graphically. And I've sort of put, do you normally tend to teach all the algebra and then link it to graphs or do it together? What do you prefer? The reason behind all of this, and I don't think I've included it on here, is we think about the graph of x squared. That's x squared. If I move it up to here, and that's number 3. So this is y equals x squared. What is the equation of this graph here? Mark.
This is going to be x squared plus 3.
Exactly, yeah. So we've just moved it up 3. In particular, the vertex has moved from 0, 0 to 0, 3. Because if I was to bizarrely complete the square on this, oh, that's supposed to be 0, sorry. I could write it like this, And I could write this one similarly. So here my vertex is at 0, 0. Here my vertex is at 0, 3. Going back to, well no, actually I'll do one more first actually. If I move the vertex to here, so let's say that this is 2. What is the equation of this graph? Mark again, since you're keen today.
Is this going to be, hang on a sec, y equals x squared minus 2x? Oh, I'm going to get myself slightly confused.
Slightly confused. You know when we were looking back at the factorising and then we were looking at the equations of graphs, this one has a repeated root. So it means it's going to have...
Yes, it's going to be x squared minus, sorry, x minus 2 squared, isn't it?
Good. Yeah, exactly. Right? So
yeah,
x minus 2 squared gives us the fact that actually the vertex has moved now, because it could, weirdly, if we wanted to, write a 0 to the end. It's now moved, the vertex has now moved to the coordinate 2, 0. So where we were looking at the equations of graphs, I think it's only natural to move on from there to thinking about moving them around and getting the different equations on that basis, so translations. Because if I combine these two things of moving left and right and moving up and down to get a graph like this, the bit inside the bracket with the squared is about moving it left and right. So because it's minus 2, it's the opposite to what you think. It's, well, to what you think, but you know, what I mean is it's not moved in the negative direction, it's actually moved 2 to the right. So the vertex would have been at 0, 0, but it's been moved 2 to the right and then up 5. So that the vertex is now at the point 2, 5. So completing the square is actually performing a translation on the graph. It is moving the graph's vertex. And so I imagine that this came first, where they moved the graph and then they were like, oh, how can we find this new equation? And they realised that through translations, they could write it down because they could think about where the vertex had moved. And then they were like, right, but if we haven't got the graph, how can we do this from the original thing? And realise that this is always half that. And therefore, if we halve this, we could then square it and see what we get, take it away, and we end up with the other bit. Anyway, that is how computing the square links to translations, and I personally think it helps to do it all together because they're all related. What do you guys think? If you were going to have to teach this, what do you think that you would be inclined to do?
I think the whole idea of actually teaching it on the graphs, as you say, is actually quite useful because that made a lot more sense about why you would complete the square once you've shown it on the graph. But that said, the school that I'm at, we don't have the facility to give them all computers to play around with the graphs package.
Right.
If you give them tablets, they could do it on their desks themselves. They'd probably end up spending most of their time looking at, I don't know, kittens slapping puppies or something like that. I have no idea. You wouldn't get them to concentrate on the task at hand.
Yeah. And Sam, were you going to say something?
Yeah, I was actually agreeing with Mark. We don't have the facilities to do that, but having tried to look at this myself, and then you running through it now with the graph, made a lot more sense.
Yeah. And it was
So,
just sort of,
so whether I'd have to do it as some sort of PowerPoint, as you've just demonstrated there,
yeah,
and added bits at a time, I think that's probably the only way to do it.
yeah. I think it's difficult because they only really need to know the process for GCSE, and that's it. And I think that's why it was always taught as just this standalone weird process that some of the kids remembered and some of them don't. And then it was only when you get to AS level that you have to know this, you know, to appreciate this understanding. But you've got to wonder whether it's difficult, isn't it? Because what is more important that they? I'm just opening this up because I'm just wondering if I've got it from the other point of view. So going from so this where I got all the other ones, but no, that's going from algebra to oh, hang on, I don't want to shut it. I don't want it. I don't want to shut it. Anyway, I think because I've normally taught it from the perspective of completing the square is graphical, I think I do somewhere have it. So if you guys do ever end up teaching it, there is definitely a lot of resources out there that can link together, that can, yeah, PowerPoint or something that you could do on the board. Yeah, you'd have to do, I think I've done it as a little mini whiteboard thing as well. I have done this where we got them into a computer room and done that. But you're right. They all go at such different rates as well. You can do it on mini whiteboards just like I've done. So you just keep questioning them. You get them, you draw a graph and you go, what's the equation of this? What's the equation of that? Why is that? Till they start to see this pattern here. And then you realise that they've got it written in this, you know, they've moved both bits. And they're like, okay, so develop the vocabulary. Okay, this is the vertex, the intex. I think that's a really good way to do it. That's sort of, you know, doesn't involve computers and is a bit more interactive than a PowerPoint, so they're all getting involved. This is part of, I think I've put a document called Quadratic Functions. It's got massive activities in there, so that probably actually helps as well. It's got the original form, the factorised form, completed square. You put where the vertex is, you put the intersects, and the, oh, so the y-intercept and the x-intercept and the sketch. And you can match them all together. So that, when you have finished the whole of quadratics, is a really nice one for them to do. Quadratics formula. So in the self-study task, is that the one that I just gave you? Or the one I'm going to give you? It was in the one that I gave you, isn't it? To prove this. Which is all about completing the square. Basically, you end up completing the square and solving it, and that is how you get the quadratic formula. This was always given at the front of the GCSE papers, so students never really knew how to use it because they were like, oh, I don't have to learn it, it's at the front of the paper, yeah. They then get to the exam and they have no idea what they're doing with it, or like what this symbol is or anything. That is simply the plus and minus written together, but students freak out in exams and they're like, what's this weird little cross thing? Now it is not given to them. They have to learn it off by heart. And as I put here, the key things they forget is that it's a minus b at the front and that the whole thing is over 2a, not just this bit, the whole bit. So their first step always is to identify what are A, B and C and then put it into here. And this is just, it's one of those things you've just got to learn by rote. Minus b plus or minus the square root of b squared minus 4ac over 2a and know it. It is just one of those things that they need to know. The bit underneath, let's see like this, the bit underneath the square root sign, let's get here, the discriminant is very useful. If you have a look at these, so have a look at these three quadratics, label each bit, so that's A, B and C. Oh, another thing that the students do is they forget about the sign because they don't really see the signs, as I'm always saying, as being connected to the numbers. So in this case, A is 2, B is -3, and C is -5. So you substitute that into working out B squared minus 4AC for each of these, and work out, it says investigate value determinant and the graph, so you need to do a little bit more because you're going to have to do the graphs. But if you start with the discriminant, I might start sketching the graphs for you, and you can see if you can make a general statement about them. Right, now for my various sketches. If you've worked out B squared minus 4AC for each of those, and you can now see the graphs of them, what do you notice about the value that you've got for the discriminant and what the graph is doing? Does anyone know what the connection is? Matt?
I found that on the first one, if the value is positive, it's what, 2 roots.
Yeah.
And the middle one's obviously a negative number, so there's only 1 intercept. And then the last one, that's 0, isn't it?
Yeah.
Yeah, so it's a repeated root.
Yeah. So the middle one, in fact, is negative, which means, thinking about it, that underneath the square root you've got a negative number, which, as we said, you can't do. You can't square root a negative number, and that's why there are no x-intercepts. There are no roots, in fact. So if it's a positive discriminant, you know you're going to have 2 roots. So when I was sketching these graphs down here, I calculated the discriminant, and I was like, okay, right, I've got 2 roots, which means that I can factorize it, so I'll do that, and then I can find the roots, and that's how I sketched it. I then worked out this discriminant, and I went, oh, okay, it's negative, so there will be no real roots. So they were technically some imaginary roots, but we don't care. And so it's going to be floating, so I then completed the square to find the vertex to help me sketch the graph. If it's equal to 0, we've got 1 repeated root. Because if the discriminant equals 0, if we go back, if we go back to this again, if that bit's 0, we've just got this number over that bit. So we've got no plus or minus. We've just got 1 answer. Hence why it's a repeated root. So there's a nice little sheet that I've uploaded again to do this one, which explores just the differences between that. And it's a really helpful guide for being able to do things. It also is used in AS level, where it doesn't tell the students, for example, what this is. It leaves it as an unknown. So it could be 2x squared minus bx minus 5. Well, normally they use like kx minus 5. Find the value of k. But it tells you what the discriminant is. So you can then say, okay, so b squared minus 4ac would in this case be k squared minus 4ac, and put the numbers in and rearrange to work it out. So those are 3 graphs, very, very, very tiny, but it's just showing exactly what I just written at. So yeah, it's called Quadratics Conclusions, which is a gapped handout that I've done for the discriminant. Also, if when you calculate the discriminant and you get the perfect square, so you get a square number, then that tells you that the quadratic will factorise. Whereas if you don't, then it means that you'll have to use a quadratic formula to do it. The reasoning being, of course, again, fairly obviously, this is underneath the square root. So if it's a perfect square, it will square root exactly and give you a whole number. Whereas if it isn't, it's going to be a bit horrible. And so you're going to use the rest of the formula to do it. 25, so we know that was square root. Whereas in that case, 13, not 13. I think I'm going to move on. This is, again, just things that you throw at them. Once they have done quadratics, you sort of say, okay, explain to your neighbour how to complete the square. Show them how to do it generically. I mean, that is really, really tough. You know, once they have to do things all letters, they don't like that. And it's not strictly necessary. This is very much extension. Finding everything to do with the thing, though, is a really good way to get them to summarise it all, and you can get them to do it in groups again with mini whiteboards or just pairs and just showing each other things. So this is what I was talking about. For what values of k does this have two x-intercepts? And they're sort of thinking, oh goodness, shall I try some numbers? And hopefully what you're trying to do is connect all these notions that they've been learning about together, because they can seem very isolated. You know that how it is in that. You do a topic, you practice that topic, and you spend all lesson doing that. You move on to the next one, the kids have forgotten the last one. So when you come to the end of the topic and you try to bring it all together, they're like, oh, that was like last week. How am I supposed to know that? Which is why I would really advocate of like an overall, always coming back, doing all of it all at the same time in this case, so they don't forget bits and pieces. It's very involved. So in terms of this one, they've got to be thinking 2x-intercepts. What do I know about that? Okay, it can factorise, but also b squared minus 4ac will be greater than 0, which I'm hoping is going to now lead me into inequalities. Because if b squared minus 4ac is greater than 0, and let's see what I've got there. Oh, no. I'm just going to roll down again. There, okay. I'll do it soon. Anyway, eventually they will be able to do this, and we will talk about this in a minute. Simultaneous equations, graphically, they need to be able to think about them in terms of algebraically what they do, and again graphically what it means. There's a really nice one here about plums and peaches, which I put in there to watch. I think it might be Marcus de Sautoy again, weighing things in order to get, the same number of plums weighing, plums having the same weight as peaches, how many of each do you need? And it's quite a nice way of looking at it. And from the student's point of view, simultaneous equations so far have just been about elimination. You've been given two linear equations, like 3x plus 4, 7x plus 6 equals something, both of them. You multiply something to make them the same, and then you can combine them. They also are asked to draw graphs and see where they cross, because that is what equations mean graphically. Now, if you can't solve them, it's because they don't cross in any way. Because equations represent functions that you can draw, they may not cross, and so you may not always be able to solve them. Again, if you are trying to solve simultaneous equations involving a linear and a quadratic, like this, often the best way with the kids is to kind of leave them to it and see what they come up with. You might get some rather funny things, but ultimately, it depends how it's written. If it's written like this and they both equal y, then your best bet is to make them equal to each other, because they are. So this is where what's happening graphically connects with what's happening algebraically in order to help us solve it, because graphically we've got these two things drawn. So in fact, let's imagine like this and 2x plus 1. So we've got our two drawings, and we are trying to find these 2 points where they cross. Those are the solutions. So in order to do that, this is at this point where students just seem to suddenly forget how to solve quadratics. They have to get this all on one side, make it equal to 0, and then solve the remaining quadratic. Thinking of a graphical solution and giving examples, explain how many routes would be possible for sets of such simultaneous equations. How could you use the discriminant to help you? Any ideas how the discriminant can link to simultaneous equations? No? Has anyone come across the use of the discriminant before?
No.
Fair enough. So, the use of it with simultaneous equations is very much the same as when we were just looking just now with looking at the crossing, the touching, or the basically floating graph. It's exactly the same with this, because if I make these, if I take it all over to one side equaling 0, for example, I get x squared minus 3x plus 2. So now, with this combined quadratic that I now have, if I find b squared minus 4ac, I'm going to have 9 minus 8, which is 1. So it's bigger than 0. When the discriminant was positive before, that meant that there were 2 roots. The difference here is that was an original quadratic when it was the roots where it cuts the x-axis. We've now combined that quadratic with a new line to make a quadratic where the roots of that equation tell us where it crosses the other equation. So this means that by the discriminant being positive, there are 2 roots, so it crosses twice. So you would expect to be able to solve this equation, which you can, and find out the 2 places it crosses. If your discriminant of your new thing was equal to 0, well, actually, I'll do less than 0. If it's less than 0, it doesn't cross. So that would be like that. What do you think is happening when it's equal to 0?
Is that when it just touches it again?
Yeah.
Because you've got the root or double root,
Yeah.
whatever you call it.
What do you call a straight line just touching a curve? You?
Tangent, isn't it?
Exactly. Yeah. Good. So if b squared minus 4ac equals 0, it is a tangent to the curve. So the discriminant can be useful. It doesn't actually tell you where it crosses at that point, but it's quite a useful measure before you set off working a load of stuff out, just to check what you're expecting and whether it's worth you going. Because if it's less than 0 and it doesn't cross, you could be spending ages trying to solve it. So, just going to look at quadratic inequalities now. An inequality is when you have a range of values that make it true, rather than just a single solution. So, here we have, find the values of x such that x squared plus 2x is less than 3. For example, if I was to try 1 plus 2 is not less than 3, it's equal to, so that wouldn't work. So it's likely that we're going to need something that is less than 1. In fact, that's probably the solution, isn't it? That x is less than 1 is going to be one of the solutions. Now, because it's a quadratic, it's probably going to be 2 different, well, there might be 2 different ranges, but all just 2 ends to a range. So it either captures it in the middle. What I mean by that is, yes, I'm going to just have the first one. So you have to rearrange it to get 0 on one side, as you always have to do with a quadratic. So you know when you're solving linear inequalities, so x plus 3 is less than 7, you need to rearrange it so you get x is less than 7. You're basically solving the linear equation with an inequality sign. The same goes for the quadratic inequality. Get it all on one side so that it equals 0, just as you would with a quadratic. And then to solve a quadratic, we would factorize it. So they say find the zeros, that just basically means solve it using factorizing. So we factorize that and it becomes x minus 1, x plus 3 equals 0. So that's if we were factorizing the equation rather than the inequality. Now that I have factorized it, I need to sketch a graph. There we go. So we know that this is the graph of y equals x squared plus 2x minus 3. We've just factorized it so that we can see that it cuts at minus 3 and 1. We are trying to solve the inequality where the graph is less than 0. Now that 0 is basically the y value. So what we're saying is we want to know when y is less than 0, when the graph is under 0. So this is where y is 0 here. So we want the bit of the graph that is under that, not touching as well, so it's not the equals, it's just under. So that is between minus 3 and 1. So our range of values which satisfy this original, so that's the same, yeah, so it's less than 0 below the x-axis. And in the exam, this is an AS, I like to get my students to like make that a heavy line or highlights or something to show which bit, just like that. So that's between minus 3 and 1. So we write that as minus 3 is less than x is less than 1. The students really struggle with this because they can't be bothered to draw a sketch and they don't really seem to appreciate what, when I'm saying less than 0 means. They tend to factorize it and just say, okay, so it must be between minus 3 and 1. But that's not necessarily true. If we'd been asked for greater than 0, that would have been the bits above the axis. And that would have been for all the bits where x is less than minus 3 and x is greater than 1. So we would have had 2 inequalities, 2 ranges. They also write these inequality signs the wrong way around. They just seem to really struggle with concepts involving inequalities. And I think it's probably where progressing into this by doing a little bit of a recap on linear inequalities and then moving into this because they do get a bit confused. Just going back, that means to this one. For what values of k does this have 2x intercepts? So if we go back to the b squared minus 4ac, the 2 intercepts will be bigger than 0. So b squared is 36 minus 4k basically is bigger than 0. Oh, this is in fact just a linear inequality, sorry. Sometimes it becomes a quadratic one because they made that the case. But in this case, we can simply solve this has a linear one common. 36 is bigger than 4k. So the range of values must be that k is less than 9. In order for that to be true, you have 2 vectors there. But if this had been the k, and another number here, we'd have ended up with k squared minus something, which would have given us more of an inequality sign. However, all of this is AS level, definitely beyond GCSE. I'm just sort of showing it to you as extension and your development. Equally, extending quadratics, sometimes they're a bit mean and they give them a quartic, but it is still a quadratic. They just have to notice that if they call t squared x, they could rewrite this as a quadratic, which they can then solve. And when they've solved that, they then put it back to being t squared again, which they can then square root to get the answers. That is really, very difficult to spot. That's really for the quite advanced students at AS level for them to notice, and obviously to have been shown. It's something that I show them so that they're aware. Because it's not necessarily intuitive, especially when you walk into an exam, you know nothing about quartics and you're expected to apply your quadratic knowledge. The quadratics is a very involved topic, which is why we're spending a whole webinar on it. Equally, how could you solve root t equals 6 minus t? Rearranging, putting it all on one side, again, we do the same thing as before. Really, this is really quite tricky to see. For anyone to see, really. You've got to let x squared equals 2, and then you can get a quadratic, and then you go back the other way again. So these are the sort of things that you would acclimatize them to, and they'll see on exam papers the sort of little tricks. And it's just experience. Okay, this is where it gets sort of really into deep algebraic manipulation. However, yes, this one, they don't both satisfy the original equation. So you have to check, because actually only t equals 4 would work. So I've uploaded some stuff, and then there's more stuff. And I've just got a little bit at the end of this about algebraic fractions. Are there any questions that you want to ask about quadratics we'll talk about in what we've done today? This is normally, at AS level, you spend at least 3 weeks, 2 or 3 weeks doing all of this. So obviously to try and do this all in one morning is very extreme. No? Okay. Well, I'm sure, with more time and practice, all of this will be more commonplace for you. Algebraic fractions is just sort of the last little bit that I want to talk about. Again, this is the sort of thing where if the students are really strong in algebraic manipulation and aren't bothered about having to do the same to both sides, they're happy just to sort of move things around a bit more, then they find algebraic fractions quite straightforward. Otherwise, a lot of them just look at it and think, I'm not doing this, I hate fractions, and now there's algebra in fractions, it's not the worst either. They've just got to think to themselves, it's all about fractions again. The same rules apply. So they need to get a common denominator. So with numbers, then they're used to that. The common denominator when you've got letters generally means that you just multiply them together, because that's all you can do. You can't generally find ones which overlap. Often those two, they overlap. But in general, you're just going to be multiplying them together. So if I do, well, I'll do this one with you. This one common denominator is going to be x plus 1, x minus 1. So in order to get that, I need to have multiplied this one by x minus 1. And at the bottom here to get that one, so x plus 1, I need to have multiplied by x plus 1. So collecting that together, I've got x plus x is 2x, and minus 1 plus 1 is here. I've just got to have a go at doing all these other ones around here. Get the common denominator and simplify the top.
Sorry, Sarah, I'm just following that one that you just did. You're finding the common denominator, but it's not simply bx squared plus 1.
Oh yeah, I can. Not x squared plus 1, x squared minus 1.
Oh yeah, cool. Yeah, sorry, minus 1. Yeah.
Yeah.
You could just have it next, but do it that way instead.
I can do that. So yeah.
Okay. That's all right. So when you start putting the brackets in, I was getting thoroughly confused. I mean, well, when you just square it, so that's cool.
Yeah. You just got to make sure that you square every bit. I mean, I'm not sure if when you say just square it.
Well, as in, yeah, just make it x squared because it's x times. Well, I can start to see how you wouldn't do that now because you'd end up with a huge quadratic, wouldn't you?
Yeah, I would just leave it until you've sorted it because you need to know what to multiply the top up by. We'll start with this one. Well, I'll start with these ones and see how you get towards those other ones.
Okay.
Sam, is your hand up to say that you've done it? Or another question?
Yeah, it is.
Okay, so what did you get for the first one? Where did you start?
The common denominator made 10, so I got 4x plus 15x, which was simplified to 19x over 10.
Yeah, makes sense. And Hugh, what did you get for this second one?
Common denominator would be PQ. So I got Q plus P divided by P over Q. Sorry, PQ.
Yeah. So it is just applying the same process that we've always done to fractions, but it's just that they are letters, that's all. And Matt, have you done this one over here?
Yeah, I've got 7x plus 18 over x plus 2 times x plus 3.
Yeah, absolutely. Yeah, I tend to leave the brackets as they are rather than bothering to multiply out. It doesn't matter. They won't. They don't mind either way. Right, this last one. Hugh, what did you get?
Do you want me to go through the working or just the answer?
I would like you to go through the working.
Right, so a common denominator would be 6x squared because 2x times 3x. So above that I've got 3x times 3x plus 4, which comes out as 9x squared plus 12x. Take away 2x times 5x plus 6, which comes out as 10x plus 12x, sorry, 10x squared plus 12x. So simplify them down, you get negative x squared over 6x squared. Take out the common denominator of x squared, you get negative 1 over 6.
Yeah. And in fact, you can make it a bit simpler. So the way that you've done it was absolutely fine, but you can in fact think of this one. So if the x, imagine that it was 1, then you'd just have 2 and 3 there. If it was 2, you'd have 4 and 6. So there'd always be this common factor of x in there. So x is already a common factor. You don't actually have to times them together completely. You can just multiply the 2 and 3 together to get the common denominator. And so that your common denominator is actually 6x. So that the extra bit for this is that you need to times this bit by 3. And the extra bit for that is you have to times that bit by 2. You still end up with minus a 6. You just don't have to end up multiplying it all through by x and then cancelling all through by x.
Roger that.
So just to be aware, it is a quicker, but also just demonstrates that you realise that 2x and 3x, for their factors of each other, they're just multiples of x, and thus you've got a common factor of x in there. So how can you solve this? Let's leave you for 1 second. What I'm saying is, if you're going to the shop, could you grab some snacks? Your biscuits or something? Okay, that's one thing. Right, sorry about that. So, how difficult to solve this? Matt? Sorry, there's a hand up from before. Sam?
Multiply by -1 and basically just swap the denominators over.
Yeah.
Then worked.
It's tricky trying to explain this to the kids because some of them are just like, yeah, whatever. I mean, you know, there's the ones that accept whatever you tell them and just happy with it. So they're not bothered. They're like, okay, so I'll multiply that by that and that by that. That's cross multiplication. They draw themselves these arrows and they just do it. Fine. Then there's others who seem to, because of the way that they solve equations, they're not thinking about moving things when they solve equations. They're thinking about doing the same to each side. So they end up with this whole, okay, I've got to multiply by x on each side, and they do that. So x and things. That's fine. Those then cancel. So they've then got 4 equals 5x over x minus 1. They want to do the same to each side. They need to now multiply by x minus 1 because they're dividing by it. Do the same on there. Oops. Those cancel. It's just a really long-winded way of doing it, but some of the kids need to go through this in order to do so. Collect it all on one side. Check that works. 4 over minus 4 is minus 1. 5 over minus 5 minus 1 equal each other. It is correct. So just a case of making sure that you allow them to do whichever they prefer. But yes, absolutely, I just think about moving those and doing it directly. So, again, multiplying and dividing is just the same as ordinary fractions. So, if you multiply, you just multiply along the top and multiply along the bottom. Very simply, absolutely fine. Sometimes you can cancel. Now, this is where the kids get confused between well, this is tricky. When I was at school, we were always taught to cancel first, simplify down first, because then it makes multiplying things easier. Whereas I think there's a tendency now to just multiply first and cancel later, because otherwise the kids get confused. And we were always sort of doing all of this, the crossing out everywhere, multiplying, cancelling and stuff. Now, obviously, these ones don't cancel anyway. But, you know, if that was a if that was a 6, then we'd cancel those first before multiplying. Whereas I think the tendency now is just to multiply it and then cancel it at the end. But it doesn't matter. It doesn't matter in which order you do those things. Key thing is multiplication is all on the top and all on the bottom, and dividing is flip the second guy and multiply. So they have to flip the second fraction and multiply across. So it's really, when you come to doing algebraic fractions, it's just a case of reiterating the fractions. And they struggle with fractions because I think it's something that they struggle to grasp, the sort of concrete concept of it. And a lot of them just loathe them. I tend to use fractions as much as possible throughout all my teaching in academic evidence, attempt to desensitize them. But, you know, force them to, they let me shy away from it. They let me forget. This is important all the way up to A level. They will always be using their fractions knowledge all the way. Probably never ever use it again once they leave school, but you know, otherwise. And I think that leads us back into how this connects to quadratics. So the reason that I've shoved this at the end of quadratics, sorry, you guys got your hands up to ask questions, or is that just left over from previous thing? If you do have something to say, please just call in, you know, pitch in. So the reason I put this at the end of quadratics is that sometimes fractions look horrible and very complicated, but once you factorise them, you can actually then cancel and get what is in fact a very simple, more simple fraction than you originally had. So whenever they see quadratics in fractions, get them to factorise and see if they can cancel. Often they'll look at them just like, but I have put again some sheets up on there. A nice jigsaw you can do where you're matching them together. And algebraic fractions does come up in GCSE, but again comes up again in AS. So yes, that was really it for today. Any questions about any of it? Okay, good. How is everything going generally? I'll ask more specific questions. Have you been able to keep on top of all the work that you've got? Sam?
Just about.
Yeah. It is fairly intensive, I imagine. And I don't know about you guys, but it's only the second week after half term, and it already feels like we need to get to the holidays. It's the winter term is also hard going with the weather and the darkness, and the kids don't, everything's not as light and easy as it is once you get to spring and summer. But when you guys, you're learning loads. Have you got assignments due for any of your things yet? Like proper assignments?
We've just had one due in on Monday. Just the Monday gone. We had a understanding learners and learning essay. So that's a weight off the shoulders for a while. I think we've got some. When is our subject audit one due? March? Is it February, March?
See, I can't. The light in my room means that it's shining on the screen, and I can't on the mouse. Yeah. Here we go. Here is the plan. Yes, I've got it down as 4th of March. So I see you in February, I think, in Bristol.
Oh yeah.
Yeah, so I see you in 2 weeks for a webinar on geometry. And then beginning of January or mid-January, I see you again for a webinar. And then intensive study week, the week after half term. And then not long after that, actually. So, you really want to have written it by, well, you want to spend your half term, I suppose, in February doing it. Now, have I talked to you about it? Just thinking about it.
Yeah, you talked to us briefly at the intensive study week. It's a bit of a haze, though. It's more of a reflection, isn't it, of where we started and where we're at now. Is that right?
It is, involving drawing in, people from research and things that you've done. Based on that, yeah, I've got this bit which has more about each of these, so I might did I show you this before? I think I've put this up in the assignment folder. So just in case you were thinking about it anytime soon. But it'll be more about when you get to slightly further in anyway. So yes, identifying and justifying your strengths, analysing areas for development, prioritising areas for development. So it kind of splits into those three things, and Carol sort of sends out a thing saying, you know, identify it, talk about it, and provide evidence as to how you know, why it's a strength, and reflect on that. And think about how you think it's an advantage, and use literature and stuff to support it. And then you kind of do the same with your areas for development. And the strongest assignments that I've seen have really sort of talked about, okay, what does it mean to be a strength? You know, using evidence, then this is a strength for me, and bringing in, you know, SCEMP and lots of people to do with maths. So I think, yes, everyone was very good at meeting learning outcomes, and a good understanding of key issues within maths. So you might sort of say, oh, I find this difficult. I find completing this way. Well, it's more of a general thing, I suppose. I find geometry difficult because I have always preferred maths as an intellectual exercise, and I'm less bothered about how things actually look. However, as a teacher, that has completely changed, because you appreciate that the students need the visual representation, and actually that then gives you a deeper understanding. And what I'd want to see is, if you were saying that, is that you would go away and find some literature where someone had said something about the fact that how we learn impacts how we teach, for example, and that we have to make sure that we use multiple representations. And there's a lot of literature that talks about, you know, the need for teachers to use multiple representations in maths. So then that's just sort of the how to bring in little bits of academic rigor, which was kind of what was missing. More analysis and contextualization in terms of sort of where things fit within curriculum and what it's like in your school and that sort of thing. But we will come back to that after in the new year. We'll come back to that in the new year. So I'll talk to you about that. Unless you're desperate to get started before Christmas, I will come back to this, and we'll go through this again in the January webinar. That's all right. I'll stop the recording now.